All right, so yeah, let's get started. So today it's my pleasure to introduce Wynn Jacobsen-Galán as our Friday lunch seminar speaker. So Wynn is an NSF graduate research fellow and finishing PhD candidate at UC Berkeley, working with Raffaella Margutti. Before Berkeley, Wynn earned a master's in astronomy at Northwestern and then a bachelor's in physics at UC Santa Cruz. So Wynn works on the progenitors of supernovae, and his expertise is on their mass loss, circumstellar environment, and he also works on flash spectroscopy and calcium-rich transients. So we'll hear some of this today, and please take it away.
Thanks, Casey. Yeah, so good afternoon, everyone. As Casey said, my name is Wynn. I'm a graduate student at UC Berkeley, and I'm really excited today to talk to you about red supergiants, their death and their life before death, through two kind of main methods. Namely, this talk will focus the first half on pre-supernova emission. So what is the progenitor star actually doing that we can detect before explosion? And then what can we do indirectly with very early time observations of young core collapse supernovae to then infer similar properties about the CSM environment and what the progenitor star, namely red supergiants, are doing before explosion. So to kind of set the stage here, for those that remember their stellar evolution classes, at the end of a massive star's life, burning, namely the fusion of different high mass elements, starts to get exponentially faster. And as we observe the progenitors of supernovae at different times with, say, HST imaging of the host galaxy before explosion, and then we look back after the supernova has gone off, we can kind of place relative timescales relative to what the progenitor star was doing inside of its core before explosion. And these are timescales that are inaccessible with stellar evolution codes and inaccessible pretty much with what we see with galactic massive stars, galactic red supergiants, because they're healthy. They have several tens of thousands of years left in their life. So we can't really use Betelgeuse and other stars in the same way that we can use the progenitors of supernovae, because those stars are not really close to death, but these stars have already died. So we're mapping the final burning stages and the final evolutionary timescales of late stage red supergiant evolution in a very interesting, novel way. And so the two kind of things that contribute to the knowledge gap that I'll be talking about today are pre-explosion imaging. That's how we uncover these kind of supernova candidates in their times before explosion. So actually looking back after the supernova has gone off or in real time to see the progenitor star itself and try to directly constrain and connect massive stars and their variety to the supernovae that we see in extragalactic galaxies. And then the second part of the talk will be through this flash spectroscopy technique, where you get very, very early time spectroscopic measurements and observations of young supernovae to see them propagate in their very local circumstellar medium, this material lost from the stellar surface in the last months, years, and decades before explosion, all probing the same very, very late stage final moments of stellar evolution. But for those of you that are interested in radio and X-ray observations as it pertains to mass loss, red supergiant evolution, or just peculiar X-ray transients and things like that, I've definitely done work on that. I just won't talk about it today. But I think that X-ray and radio studies are a very, very promising field for understanding mass loss and just circumstellar media in general. Okay, so the first thing I want to talk about is the direct detection of what we call pre-supernova emission. So what is the star doing that we can actually detect and gather photons from with ground-based instruments? So the key is that we actually are in this really amazing era where ground-based surveys, ZTF, Young Supernova Experiment, ATLAS, Assassin, DLT-40, all sky surveys with 1 and 2 meter class telescopes, so pretty small, now have the potential to observe the pre-explosion outbursts or pre-explosion emission from the progenitor stars prior to supernova. And so this is a really nice compilation from the ZTF collaboration focusing on type 2N supernovae. So these are supernovae that interact almost for their entire evolution with dense circumstellar material. So that means that their stars underwent extreme mass loss episodes. And that's kind of confirmed by the fact that we're observing the outbursts actually prior to explosion, given the sensitivity of ZTF to these objects. So the kind of whole holistic picture is that these stars are probably, extreme LBV like progenitors, or maybe Wolf-Rayet stars, or in a binary, and the outbursting activity is actually detectable, and it's probably the origin of all this dense gas that the supernova itself is trying to work its way through for years almost. So these are very extreme events, and that's kind of been the kind of phase space observationally so far with the like objects we've discovered. But I want to kind of bring that into kind of a new regime with understanding more normal progenitor stars with ground-based surveys. But physically, I think it's worth noting like where is theory gone with these kind of observational I guess probes that we found. And I think there's kind of like three main mechanisms in a massive star that we've thought about and done simulations for to try to understand how do you get such enhanced pre-supernova emission well beyond like the Eddington luminosity of a massive star. So this is an outflow. This is a true unbinding of material. And one is very simple and doesn't really require any extra like physical intuition about what the star is actually doing. It's just take the binding energy of a massive star and put the binding energy plus a little bit more right into the envelope, and then you unbind the envelope. And this creates a very luminous precursor event, very luminous like mini supernova, but it's basically just all recombination and just the thermal emission of the envelope. And so we've done this really well in 3D. We just inject some stuff into the envelope and we power this kind of luminous precursor. And this is kind of the outburst scenario. But I would just want to caution this where we're really good at making this scenario fit the observations, but there's not something physically rooted in stellar evolution yet that could lead to this. Is it something that's happening in the late stage burning? Can we propagate that energy in these late stage fusion processes to the outer envelope to then unbind it? No one's really done that in enough detail. The other mechanism that actually is more rooted in these late stage burning processes is the gravity wave scenario. So Jim Fuller's group, Samantha Wu at Caltech, they've worked extensively on this and found maybe not so, I guess, consistent results with the pre-supernova emission, but still found that gravity waves during neon and oxygen burning can definitely take energy into the outer envelope, but not enough to really unbind a lot of material. So these progenitor stars with gravity waves, it's not really the best mechanism for driving material off the surface. Alternatively, for very extreme stars, you can kind of have this like heating of the base of the envelope to drive this like super Eddington wind. That's something that's been explored, but it drives something very steady state. It's not something that happens as a dramatic outburst. So this is something that would be kind of continuous. So this was kind of the phase space before, maybe for the first couple of years of understanding this. I kind of used a new transient survey to kind of explore this in more detail with this pan-stars all-sky survey called the Young Supernova Experiment. And it wasn't designed specifically to discover precursor events, but the first part of this talk will be actually using the pan-stars sensitivity to detect things that ZTF and other a little bit shallower instruments couldn't detect, but pan-stars could. So this is a transient all-sky survey designed to supplement ZTF and other surveys to try to get like daily cadence down to pretty deep magnitudes in GRIZ filters. So more colors, more sensitivity. It has a lot of science cases, so if you're interested, please come talk to me. It's still an active survey. And so early in the survey, it started in 2019. Early in the survey, we detected this pretty nearby supernova, 2020 TLF. We got really excited because it was one of the more nearby events that we had found with YEESY. YEESY stands for Young Supernova Experiment, so I'll probably just say YEESY. Basically, before I get into the pre-supernova properties, I just want to list and put in everyone's mind just what we inferred from the supernova itself. So we saw this young event. We triggered a Keck TOO, and we got this first spectrum here. So it's this hot blue continuum with these really interesting narrow emission lines that are direct evidence that the star, after exploded, collides with dense circumstellar material. So this is already looking like some sort of interacting supernova at early times. It goes behind the sun, it reemerges, and it looks more just like a type 2P, so something that we'd infer from a red supergiant explosion. So the hypothesis that, and based on modeling and other properties of the supernova itself, is that this is a red supergiant star. It exploded in a nearby galaxy in some dense confined CSM. it's kind of on the smaller side based on the nebular spectra. These are all properties that I could go into more detail, but I think it's more interesting just to put them out there and then think about how they relate to the really cool, interesting, unprecedented detection of pre-supernova emission for a normal type 2. Because YEEZY observes the field both before and after explosion, we have really nice deep limits on the persistent or the detection or possibility that the progenitor star could have been detected before explosion. Yes. Sure. Oh, sorry. This is supposed to be 2020. Yeah. Thank you. Good. Yeah. Yeah. No, thank you. Yeah, that's true. That's true. I think someone's actually pointed this out to me too before, and I always forget to change this plot. But yes, thank you. No, you're good. You're good. It was detected before explosion, and yeah. So we had this really nice baseline of at least a couple years before explosion, and I kind of noticed something interesting in the data where there's these kind of possible detections before explosion, but because this was seemingly a normal type 2, which we had never detected a precursor event before, many people were kind of like skeptical that I should really look into this. So I kind of like bugged enough people and pestered enough people. And it turned out that actually there is this really high confidence, high signal noise detection, where you see in non-detections here are all the like transparent signal photometry points. But then there's this rising flux that happens about 130 days before explosion in some of the reddest filters. So I band, R band, Z band. So this is a really red, not blue, pre-supernova emission in the last half a year before this red supergiant died. And to really confirm this, we do template subtraction with pan-stars. So you have your really deep template where there's nothing there. And then you stack all of your images down for when you want to be looking for this pre-supernova emission. And we subtract the two, you see this super luminous detection of not a supernova and not a explosive transient that's terminal, but rather this is the red supergiant itself doing something really, really dramatic before explosion. Yeah.
Wondering, so is it true that the transparent rectangles are upper limits on the flux?
Yeah, we plot them as like
oscillates very rapidly the emission, or?
Yeah, I think it's worth noting that there's potential for some variability there, but I don't think that it's actually significant enough that we can constrain that with the data that we have. I don't think that I think that there may be variability there, but I'm always just like cautious to claim that with these detections. Like the detections are there, but the behavior of the detections, we're really pushing the sensitivity of the image here. So yeah. But keeping in mind variability and other things, that's something that we should be able to detect, like with future events for sure. So we have this really luminous source. This is the red supergiant itself undergoing something not terminal, but rather really enhanced, and this rising pre-supernova emission. And what we get to do for the first time, and as supernova scientists, we usually like start at T0 and we only make light curves that kind of extend this way. But now we're in the era where we can build seamless transitions between the progenitor itself and its activity all the way through explosion. So you have this kind of super Eddington, pretty luminous, pretty flat precursor, but keep in mind that this is like a pseudo-bolometric light curve because it's a pretty red event, but we don't have detections across the SED, so you have to just always be like state that as an disclaimer. But definitely this pretty luminous precursor emission. The supernova goes off. It falls on its plateau phase, which is common of type 2 supernovae, where the powering mechanism is the hydrogen recombination of the hydrogen-rich material that's ejected in the envelope, and then it falls on this kind of normal radioactive decay tail. So this is from, if I only looked this way, it would look like a pretty typical type 2 in general, which is really cool. So for the first time, we really had this red supergiant that we know was the star responsible for this supernova, and we observed this kind of pre-supernova emission. Yeah.
Read anything about that your precursor emission, those temperatures get up to like 5,000 Kelvin?
Yeah. 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 So I mean, those are like, since it's a black body temperature, it's just like the thermalization at the thermalization depth of whatever's emitting, but it's warmer than a red supergiant. So this is likely, I think, in my opinion, is material that's ejected. Maybe it slams into other material. Maybe the outburst itself is clearly, very high temperatures. So it's well beyond what the red supergiant surface. So that was a big thing that we had to like conclude, was that this is not the star just undergoing like some sort of oscillation or expansion or something happening. And especially not like on the dynamical timescale of a red supergiant. It's something that is really like, it's non-terminal, but it is explosive or an outflow of some sort. Yeah, which is something that we did not think red supergiants were capable of. Yeah, cool. So putting it all together with some fun animations, we have this pre-supernova detection of the red supergiant itself. The red supergiant is about 10 to 12 solar masses in its zero-age main sequence phase. Modeling of the light curve and the early time spectra kind of give us this enhanced mass loss rate in this confined shell of circumstellar material, but then it transitions to this normal type 2. Following this precursor event, it explodes. It kind of has this luminous early time light curve, but overall type 2 supernova 2020 TLF. Yeah, so this was a cool test case. It showed the capacity of other ground-based surveys to detect precursor emissions from seemingly more normal explosions, even though 20 TLF definitely had its idiosyncrasies. But the goal now, and something I'm working on with two really talented Berkeley undergrads, is building kind of a systematic pipeline to detect this in the entire YEEZY data set that we have. So we have almost 4 years worth of pre-supernova data for a lot of objects. So we can be unbiased in what we look at. We can derive really nice limits, or maybe find really nice new detections of things. So I think this is kind of a preliminary plot just based on a few objects that an undergrad worked on over the summer, but there's really significant variety in the pre-supernova signal for a lot of objects and a lot of supernova subtypes. So type 1b's come from Wolf-Rayet stars, type 2's come from red supergiants. So red supergiant, red supergiant, red supergiant, these are limits. So there's very quiescent red supergiants, there's very extreme red supergiants, there's very extreme Wolf-Rayets, there's very extreme LBVs. I mean, what you're looking at here is kind of a stellar evolution plot, really, if anything. So I think it's really, really promising. And we're going to have more data than maybe the models can keep up with. So I think that this is really a fun time to understand the rates of these events and prepare for what will happen with LSST, which should uncover these no problem. Yeah, so before I transition to outside of direct detection, I just want to pause, take a breath, and then move on to supernova science a little bit more.
I'm curious, have you tried to look for these precursors where you didn't detect the supernova? So there aren't reported supernovae?
Yeah, so almost like predicting the supernova itself.
Just
yeah.
Look at other parts of the same galaxies and see whether you see precursors without having a reported supernova.
Yeah, that's like the crystal ball dream that we would have. We would actually see a precursor in real time and say, this is going to be a supernova, or this star is doing something dramatic. We're not there yet, but I think with YEEZY, it's possible for nearby enough galaxies, and I mean like really like less than 30 megaparsecs. ZTF probably the same, but with with LSST, 100%. This is something that came out of this that exact thought, and I think it's super amazing. It's almost like too good to be true to predict a supernova, but yeah, maybe. I hope so. That would be amazing. Yeah.
To follow up on this, what does the SED look like? Because it looked like it wasn't going to be a black body.
Yeah.
So it might be something to filter on, right? If it's not a star, that might be something like it should be popping out, right?
Yes, definitely. Yeah. So we're trying to really focus on infrared, also combined surveys to you understand the infrared portion of the SED, because presumably these things should be, at least the red supergiants are very cool. So if we're looking for those plus their precursors, it's going to be anywhere from peaking in the infrared all the way to maybe just like the near IR. So we should have a really decent constraint. Pan-STARRS goes GRIZ, so it goes out to maybe like 1 micron. But if we had an infrared also survey to do like J, H, and K band, it would be really, really important to understand that SED. And yeah, for 20 TLF, the SED is like definitely not very well constrained, so the temperatures have to be taken with a grain of salt. But there is definitely more events where it's almost like a bluer emission. There's going to be blue and red, I think, precursor events. So something with higher temperatures, something with lower temperatures, and it's going to really have to link to what's happening physically with this pre-supernova emission mechanism. Yeah.
This is a really neat plot. I'm looking at it and I'm seeing the horizontal line at about absolute magnitude of 12. If you're not seeing precursors in before about 100 days.
Oh, this, yeah. Oh, this here.
Just like it looks like there is an upper limit at about an absolute magnitude of -12.
Yeah.
With the exception of like the very last 100 days. You know, we have this like issue with supernovae where we're not seeing progenitors above the log luminosity of like 5 or so.
Sure.
Are these related at all? Is this I can't do math in my head,
Yeah.
but is -12 correspond to anything like that upper limit that we're seeing with the supergiant problem?
Yeah, with the red supergiant problem, -12 is well above that. I mean, like I guess, supergiant star is typically like 10 to the 5 or yeah, almost -7, -8, maybe even lower probably. So a quiescent red supergiant is much below this, and we're just not really doing anything constraining for just red supergiants in isolation and quiescence. But for example, like this is just a couple data points from a very nearby type 2 at 7 megaparsecs, and we can push down to -7 magnitude. But in terms of the red supergiant problem, I think you need infrared measurements, because I think the red supergiant problem as a problem may be in more like an indication of what we don't understand about dust and mass loss in red supergiants in general. So yeah, I just listen to the red supergiant people and tell me like if some people, really talk my ear off about how it really is a problem, then other people are like, you just need to, don't worry about it. Yeah, exactly. Yeah, or it's not a problem. Yeah, I don't know. We're going to definitely try, but I just don't feel like with a ground-based survey like Pan-STARRS and Yeezy, we'll be able to really place constraints. But there's a really nice like preparatory study of what LSST could do with quiescent red supergiants, and we should be able to really see those progenitor stars very well. So there's a whole regime of progenitor system studies that should come out of LSST. Yeah, cool. All right, awesome. Okay, so shifting gears a little bit. Speaking of galactic red supergiants and what we see with red supergiant progenitors, there's kind of a classic picture that we had for a while, in that the mass loss rates of red supergiants are definitely uncertain, but they're uncertain going in the opposite direction. They're actually lower than we think. And so there's been a lot of really nice work by like Emma Bieser and Ben Davies and other people that really look at red supergiants in the Milky Way and other places to really understand how well do we understand their mass loss rates. These are healthy red supergiants. They're not really close to death, but these mass loss rates are then forward modeled and used in our models to just kind of be a systematic in our understanding of stellar evolution. Then, as I mentioned before, we actually have detections of type 2 supernovae, so the red supergiants before explosion themselves, and they do align with this kind of quiescent, weak mass loss picture where they're not like the 20 TLF precursor I showed, but they're very well-behaved red supergiants. So these are kind of typical red supergiant magnitudes as detected in pre-explosion imaging. So in type 2 supernovae in general, for a long time, were thought to just arise in a pretty clean environment that's only really polluted by a typical red supergiant wind that's driven very classically, just a line-driven wind at 10 to the -6 or so solar masses per year or weaker. So that was kind of the classical picture for a while. But then with supernovae, we started to find objects that completely like upset that paradigm, which is through this flash spectroscopy technique of observing young type 2 supernovae within days of explosion, as the shock is really just sampling the very closest circumstellar material to the progenitor star And this is the material that was lost in the last months to years before explosion. And what we're inferring is extremely high mass loss rates, like orders of magnitude higher than a quiescent red supergiant, but using a terminal event, using their demise as the probe of this pre-explosion environment. So flash spectroscopy means really just getting on target in a flash and observing the earliest supernova spectrum. And so a normal type 2, if it was colliding with a pretty weak wind, would not show these high ionization emission lines. These emission lines actually come about because of photoionization with dense circumstellar material. And so we found a good amount of these events. It's been a pretty popular avenue of time domain astronomy for almost a decade now. And we find one event, we write one paper, we infer one mass loss rate. It's good. This is like really, this is very like important science, and I've done the same, one object, one mass loss rate. But we're now at a point where we're systematically finding these things, and we actually have a really nice like archive of these events that we can model very well to understand what is like the whole population of red supergiants that explode in dense CSM, and how does it compare to the quiescent red supergiants? Are there distinct populations? Are red supergiants like weird in one mass bin, or are they weird in one time scale? Or is it a continuum where we're just seeing red supergiants doing different things as a function of their mass or their radius or something like that? So that's kind of what I wanted to uncover. But before I do that, I kind of want to walk through kind of a little bit of math, like even that I can do as an observer, to kind of give a physical intuition for why these lines are so important, even without fancy hydrodynamical simulations or radiative transfer. And to do this, I kind of want to walk through like 3 test cases for the circumstellar material around a red supergiant as a supernova shockwave goes through it. So this is a pretty typical red supergiant like density structure here. And then it cuts off to either a weak mass loss. So this is like as if Betelgeuse exploded. This is its progenitor environment. This is a more extreme mass loss environment, 10 to the minus 2. And this is like a very, very extreme, like almost a solar mass worth of material lost in a year. These are the 3 test cases that I want to go through and what it looks like observationally if I send my supernova shockwave through it. Because with these 3, you pretty much have all you need to understand the diversity of red supergiant explosions and their environments. So the first, let's explode let's see what Betelgeuse would look like if it exploded tomorrow. So you have shock breakout from the stellar surface. We have a very nice history of understanding shock breakout. It's getting better. But just the best thing to understand is just when do we see photons? It's approximately an optical depth that is the shock velocity over C. And then the characteristic temperature and energy that I get from this like very high energy burst of X-ray and UV photons is kind of defined by these shock breakout physics that I won't get into, but it's definitely a really nice field of study. So shock breakout photons, and then the circumstellar material in blue. Because these are such high energy photons right away, they're just going to cook all the gases. It's going to photoionize everything. Everything's going to get ionized immediately through this kind of like flash ionization. And in kind of steady state with no additional like light bulb behind it, no additional photoionizing source, your recombination time scale, so when will these atoms then grab an electron back and recombine, is approximately 1 over the number density in the gas. And in steady state, that should be kind of like connected relatively, in equilibrium with the ionizing time scale. So as these things recombine, they emit their recombination photons. And if I were to take a spectrum of Betelgeuse at like 0.1 days, like an hour after it exploded or something, I would see a hot blue continuum for sure, and maybe a couple narrow emission lines from the recombination of these atoms. But this is really hard to do. This isn't like a timescale that we can't access right now as observers, but this is kind of the flash ionization picture. So over time, this material in the circumstellar environment will be swept up by the expanding supernova shockwave. It'll build up this thing called a cold dense shell, where you have your forward shock moving outwards and your reverse shock moving inwards. And it's in space pretty actually small of a regime. So this is kind of like made larger, but not to scale. You'll have some like really cool Rayleigh-Taylor instabilities. This is a really like interesting structure in the ejecta CSM kind of interaction. So this will sweep up some material, but observationally what we'll see is kind of just hot blue continuum, and we'll start to see absorption and emission lines from the supernova ejecta pretty immediately. So within a day, I mean less than a day, you're already starting to peer into what's swept up into the CSM, from the CSM into this dense shell, and then just moving into the supernova ejecta, which is just the red supergiant now unbound going out into space. Okay, so for a normal red supergiant, it's not very interesting in terms of its early time spectrum. Pretty hot blue, we can understand temperature, but not a lot about the circumstellar medium really, because we can't access these timescales as observers. And then over time, we'll continue to form these broad lines, and qualitatively looks pretty nice when we compare to observations. Black is a young type II supernova. So that case is pretty well understood, but hard to access if you really want to understand like direct detection of CSM interaction, like these flash ionization lines, this flash spectroscopy technique. And to do this, we actually need higher mass loss rates to keep these lines illuminated. So how do we do this? Same thing, shock breakout. You see the recombination just from the shock breakout pulse, takes all these atoms, strips and electrons recombine, and produces a very different looking spectrum at, again, less than a half a day after explosion, where you have this forest of beautiful emission lines coming from the recombination of much more dense material in the circumstellar environment as they have been ionized by the shock breakout pulse. But still, as an observer, less than half a day after explosion is not a timescale that I can access. But if I wait past the flash ionization phase, and now I move into the photoionization phase, where the shock wave is actually providing now a lot higher luminosity to keep photoionizing my gas because the densities are that much higher, then I can keep these lines illuminated for timescales that I might be able to access, like 1 or 2 days after explosion. And so this is kind of maybe already familiar because I showed all those early time type II observations where these exact lines are present. And this is an indication that we have a shock wave propagating through just that much denser of material, that we can then see the continuous photoionization of this gas. And what's kind of cool, I think, the most interesting thing about this process is actually what's happening with the free electrons in the gas. So if I let one shock photon out and it photoionizes my hydrogen atom and the hydrogen atom recombines, it actually is going to go through a lot of scattering inside of the gas, because inside the gas, we have to remember that it's pretty high density and it's been ionized. So there's just free electrons just all over the place. And free electrons don't like photons to get out very easily, especially if there's a lot of them. So just through electron scattering, this photon's actually going to work through kind of a tough environment to get to me and my telescope. So this is kind of some simple, relatively simple like relations between that. And pretty much the thing to take away is that if it scatters one time, I'm going to get a velocity in my emission line that's characteristic of the thermal temperature of the electron. So how hot is the gas and the electrons in it? If it scatters many times, it's that thermal temperature times the optical depth, pretty much. So I'm not a theorist, but I can understand that. I can understand that math kind of. But so if we do this again, and we look at the observational signature, we form this kind of almost delta function looking like single emission line whose width is characteristic of the thermal velocity of the electrons. But then as multiple scatterings happening, I see this broadening in the line that's indicative of this electron scattering process. So what's actually happening here is not related to the dynamics of the gas at all, but rather the phase shift that this photon is experiencing as it's working its way towards us. It's being scattered and blue shifted and red shifted and blue shifted and red shifted by these free electrons. And the optical depth in the gas is the reason for it. So even just looking at one emission line and just with pretty simple approximations, I can understand the density in a red supergiant's environment as the red supergiant explodes and propagates through it just because electron scattering is the dominant process. So I think that's pretty powerful because over time, as the lines fade away, that's when the CSM stops being so optically thick to this electron scattering. And now we have this really nice transition point where we have optically thick, very dense CSM. And then if these lines fade away, the very narrow Lorentzian profile lines, then electron scattering is stopping being the dominant source in the CSM. And I'm starting to form my photosphere deeper in. And so the CSM interaction, as we saw it at early times, is now ending. So this is a really nice probe of how long before explosion did this red supergiant emit this intense or undergo this enhanced mass loss, because we're seeing the supernova shockwave actually tell us in real time that there's no more dense stuff. This is the edge. So that's the time scales under which this progenitor star did the craziest stuff. And then as it transitions away, we can see just starting to see the broad lines of the supernova ejecta appear. So one last limiting case that's, I think, less intuitive, but really worth noting, is that if you put too much stuff around a red supergiant at the time of explosion, you won't see these narrow emission lines. So our community has definitely utilized the stacking of a lot of material around red supergiants in simulations to try to reproduce the early time light curves. But the inconsistency there is that if you put too much stuff, the mean free path of your photons inside all of this stuff becomes so short that it's much less than the size of the CSM. So those photons just stay trapped. So it's like if you tried to recombine, the recombination photons can't work their way out of anything or even do electron scattering. So I'm just going to see a hot blue continuum. Yeah, OK. So this is really the most extreme picture, just to keep in mind that it's not really like enhanced mass loss rate or weak mass loss rate. It's actually a very nice continuum where there's a delicate balance in how much density needs to be there for me to see these like very prominent photoionization signatures in the early time spectra. OK, so that was a lot of the physics. But going on to the observation, I think now we have like a framework for like what's happening phenomenologically, where as the optical depth drops in either case, that's when these lines fade away. So now we can look at observations and see exactly how that physics kind of translates to what we see with time series early time spectra. So if we take early time spectra of a type 2 supernova, you see these narrow emission lines broadened by electron scattering at a day and a half after explosion. And then we can actually see in real time, if we have high cadence spectra, the transition between optically thick to electron scattering to optically thin, like kind of around here. So now we're starting to form these more like broadened, Doppler shifted profiles that come from the faster moving supernova ejecta rather than forming a photosphere in the CSM. So this timescale is exactly the same timescale that I was talking about before, where that's the timescale over which the shock sees dense stuff and then sees lower density stuff. Yeah. So what I'll talk about last is kind of the ultimate goal of taking all of the flash spectroscopy events that we have so far. It's approximately 60 or so that show these narrow emission lines. This is a subset here to kind of show the diversity. But what I have done recently is just kind of gather up all these objects, as well, published and unpublished, to try to see what is actually the diversity amongst this whole, not systematically selected. There's no volumetric reason why these objects are selected, so there's no real rates that can come out of this yet. But just to see that diversity, and also very importantly, linking it with swift UV observations so that we can get a full SED of these objects at early times. And I think the UV is probably one of the most important. So even observationally, it's really cool to see that the narrow emission line signatures that we see at approximately the same phase for all these events that come from red supergiants that then transition into type 2 supernovae, there's a lot of diversity. And I think that it's really a nice continuum of events where you just have different mass loss rates, different CSM extents, and you can build this kind of continuum of what red supergiants are doing before explosion, just looking observationally and not applying models yet. So looking at the populations, we have very enhanced UV luminosity amongst strongly interacting objects with these clear lines. Then we have a control sample with no emission lines, so that's more of your typical red supergiants exploding. These are more of your extreme red supergiants exploding. Maybe you have this continuum here. And I think swift and UV emissions are extremely important because for CSM interaction, as you let a forward shock thermalize over your whole CSM shell, the temperatures that you see as an observer peak very directly in the UV. So without UV observations, CSM interaction is really not well constrained. Yeah, so this is kind of the observational picture. And the last thing I'll talk about is how to infer mass loss rates from application of radiative transfer models. Together with collaborator Luc Dessart, who's in France and is the expert of CMFGEN and the Heracles hydrodynamical simulations, we built kind of this rough grid of different density structures that then we can blow up a red supergiant into and make all these synthetic spectra and synthetic light curves shown in black compared to like the continuum of observations we see. And the goal was to try to extract mass loss rates, CSM densities, CSM properties for a wide variety of these red supergiants where we know CSM interaction is happening. And so that's what we did. So we fit radiative transfer simulation in red to these early time spectra, as well as matching the bolometric light curve and multiband light curves as well, because CMFGEN can really do it all and produce both photometric and spectroscopic observations synthetically. And we kind of build what I think is a preliminary continuum of red supergiant mass loss as a function of an observable, which in this case is the duration of these photoionization signatures. So the black squares here represent the control sample where there's no lines detected, so they're upper limits, but you'd assume that maybe if the models were correct, these are the weakest mass loss rates, and you would maybe just see the flash ionization phase, but no actual photoionization because the densities are too low. But then you have this kind of continuum all the way up to the most extreme events where you can keep these lines illuminated through photoionization for longer, indicating that some red supergiants experience very dramatic enhanced mass loss rates compared to weaker ones. So to conclude, I kind of wanted to go back and just think about the future and of both the detection of pre-supernova emission and flash spectroscopy. So just kind of my 2 cents on pre-supernova emission. I think we need to work together, observers and theorists, to build more physically motivated models. Let's go from what stars are actually doing in their cores or at their surfaces and actually predict the precursor signal based on physically motivated scenarios. And then large data sets, LSST. So this is 20 TLF and its precursor event. LSST would see this no problem out to 100 megaparsecs, and we'll discover these events in great detail. But yeah, the physically motivated models, we want to look at the core structure and what it's really doing at the cores of these stars and how it translates to what's happening on the surface. But this is hard. This is not an easy thing to do. For flash spectroscopy, this is something that I'm working on actively right now. I want to build up our model grid to be more high resolution so we can really have low error bars on the mass loss rates and densities we infer from red supergiants that then interact as they explode. Volume limited samples, so I can actually give you a rate of enhanced mass loss rate amongst red supergiants in the local volume would be extremely powerful, I think, for stellar evolution. And then I'll still plug the UV. UV missions, TOO programs on HST to get UV spectra. So just in black is what we can see with this interaction in the optical, but there's so much more we're missing in the UV. And this is really an amazing unconstrained phase space that we'll access with future missions, hopefully. And I think the future is also right now. So there was a supernova in M101 that 23 IXF that showed these narrow emission lines. We detected the progenitor star itself. It was this undulating, pretty low luminosity red supergiant. We have multi-wavelength detections understanding CSM interaction. And this is kind of going to be the prototype for CSM interacting type 2 supernovae for at least, I think, the 21st century for now. So we have a lot to learn from this and then apply to extragalactic red supergiants that explode. And yeah, I think there's quite a bit that we can maybe change about how we think about things that don't have such exquisite data sets as 23 IXF. But yeah, a little plug, if you're at AAS this winter, I have a special session that I'm running just on 23 IXF. So if you want to hear about all 40 people that wrote papers on this object in the last 3 months argue about mass loss rates and progenitor masses, I'll be there. So come stop by. And with that, yeah, I will take in questions, and here are my conclusions.
Okay, so we got a lot of questions during the talk, but we have time for maybe one quick question. Anybody have on the second part of the talk?
I feel like I've hogged the questions, but so you have this really neat TSM or CMFGEN grid,
Mhm.
and you said you can blow up a red supergiant into it, which I'm assuming just means like run a shock through it. Do you expect that the properties of the underlying red supergiant will affect how that process works? Because it'd be really neat to tie in these mass loss rates and all the other things you're inferring with the actual properties of the progenitor.
100%, couldn't agree more. Yeah, so for the initial grid that I talked about, that's in the paper that we are just putting out, we kept it really simple. We just varied the CSM densities and extents, but we kept a pretty normal red supergiant, 15 solar mass, blew it up with 1 × 10⁻51 ergs explosion. With a new grid that we're making, we're going to vary the extent of the red supergiant, the size of the red supergiant, the metallicity. We're going to vary the explosion energy, and then we're also going to vary the CSM properties on well. So it's the grid itself will be like almost 1,000 different variations. It'll be fantastic. It's computationally intensive, so we're just working on that right now. But yes, right now we could only do CSM properties, but maybe there's a link with progenitor properties too. Very cool. Yeah.
Cool. So yeah, thank you everybody for coming. Let's thank one more time.